We are privileged to be using the, based on the territory of the Senchothan speaking peoples. This is Wetixis in their language. And we are hoping to actively work with the local First Nations. All right, that's gone now. Okay, I've been waiting for this presentation for a while. I'm pleased to introduce John Pazder, who is a world expert in optics for astronomical instruments and telescopes, and he works right here at DAO. He's been designing and building astronomical instrumentation for the last 30 years and has recently spent a lot of time in Chile with the GHOST spectrograph, actually putting it in there, which he's going to talk about tonight. On a personal note, I first met John as he was my student when I was a lab demonstrator about 30 years ago, show both of our ages. Yes. And I have this memory of John giving me a ride somewhere, and he had built this electronic tachometer in his car. And he just put this all together himself, and it was, to me, who has exactly zero proficiency in electronics, it was just out of this world. He's been exceptional for a long time, therefore, and I'm very pleased to introduce him tonight. And you have the stage.
Well, thank you very much. And you bring back memories of when my speedometer cable broke and I didn't have time to go to get one. So I built one. Okay. It was about GHOST. And GHOST is it's the newest spectrometer for the Gemini 8 meter telescope. But first thing I have to do is explain to you what Gemini is, because some of you may not know what Gemini is. And then I'm going to try to explain what spectrographs can tell us about the universe. And lastly, I'll tell you about the GHOST instrument. So Gemini, as we all know, is the twins. And around 1999, these two telescopes, which are twins of each other, were built. One in Hawaii, and the second one in Chile. Now you may ask, why do astronomers want two telescopes? Well, the Earth is round, and if it's round and you're at the top of the Earth, you can't see things on the bottom. So you need one telescope in the northern hemisphere, that's the one in Hawaii, and one in the southern hemisphere, and that's the one down in Chile. So I'll be talking about the one in Chile, and they're almost exactly the same, but slightly different. Now, Gemini is big. It's a big dome. You look at this picture, you see that bus? That's a full-size bus. See all those stairs? It's 15 stories high, and it's about 120 feet around. So your average house in Victoria would fit inside that dome. The mirror itself is 27 feet. There I am standing under it. That's 27 feet around, 8.1 meters. It's big. The amount of light it collects is 1 million times more than your eye will collect. So we know what Gemini is, but why would astronomers want spectrographs? Well, astronomers' job is to figure out what the universe is. And this is this beautiful picture from James Webb. And you can see all this stuff there, but really, I mean, how do you know? You ever play that game, you know, you get the little picture and it says, what is it? And you have to figure out what it is. Well, here, we got this picture of something, like, how do we know what that is? We can't touch it. We can't smell it. We can't pick it up. You know, and your mom said, keep your hands in your pocket. But astronomers have to keep their hands in their pocket. The only thing they can do is look at it. So how do we know that's not just fireflies up there or something? Right? You know, how do we know the physics here is the same as the physics there out there? So one of the ways you can figure this out is with a spectrograph. So the first thing is,
sure, need to be a bit more sensitive. Maybe we will put it like this. it's
Sure.
comfortable.
No, it's fine.
Wait, sorry.
Okay. So the first thing you have to understand is just the color of something tells us about it. I mean, blacksmiths have been doing this for centuries. They look at the color when they heat up the steel. And when it's a straw color, they know it's time to pound it. Well, if something's kind of cool, it's red. And if you look at Betelgeuse up there, that's a red supergiant. It's only about 3,300 degrees Celsius. It's nice and cool and red. Down in the bottom corner at Rigel, you have a blue supergiant. Well, that's a much, much hotter star. So as you start to get hotter, it goes from red, starts to turn white. Unfortunately, I'm not going to turn this past white because when it turns blue, it's usually burning out. So just from the color, we can tell the temperature of the star. And you see that big fancy diagram up there? That's black body radiation following Planck's law. It's basically a lot of physics says when you warm it up, it turns blue. When it's cold, it's red. So the first thing astronomers figured out is, hey, we look at stars just by the color, we can figure out they're hot. Now, a couple centuries ago, when they looked up there, they said, well, we know the sun's hot. It's glowing hot, but they didn't know what powered it. They didn't know what it was made of. Actually, some people thought it was made of coal, and it was coal burning. That wouldn't be good for greenhouse emissions, would it? Now, around the 1800s, there was a real revolution, and the first person to really study this was Fraunhofer. And Fraunhofer was sitting there in about 1814. He was looking at the sun through a little spectroscope. You can see is looking through there. And he was looking at the sun. He saw all these lines, little dark lines. And those lines were superimposed on the spectrum of the sun because he was able to resolve it. Now, Newton, a while before this, he was a very famous person. He also looked at the sun, but he didn't see those lines. Now, one of the reasons he didn't see the lines is that when he put an aperture, he put a round aperture for the sun. If he had put a slit, a narrow aperture like that, he would have saw those lines. And that would have changed science a lot. So he saw the lines. He said, well, this is curious. And he studied, he cataloged, I think it was 300 or 500 different lines that were there. But it wasn't until about 1860 that this fellow Kirchhoff, he was looking at this and he noticed that the sodium D lines, which are these two lines, I can't quite point them out from here. Those two lines, he was looking at those, and when he put salt into a flame, he saw the same two lines in the same spot. And he said, hey, I wonder if it's the same. Then he managed to make it so instead of being really hot, he made it cool and he made it so it would absorb. So he saw two dark lines instead of two bright lines. He says, I know it. That on the sun, there's sodium. And shortly after, within 4 years, he found sodium, he found calcium, he found manganese, he found chromium. And all those lines correspond to all these elements. Now, this is pretty incredible. Just by looking at a rainbow, you can identify elements on the sun. And you know those elements in the sun because when we are on the Earth and we either put those elements in a flame or something, we see those lines in the same location. Now, how are those forming? It's forming because the electrons in the atoms are bouncing back and forth. So if the electrons are in their little orbits close to the center and light hits it, they jump up. But for something to jump up, you have to give it energy. And giving it energy causes it to absorb. But because they can only jump between two lines, it makes very specific absorption lines. Now, if they fall down, it emits light. What this tells us is the physics on stars is the same as the physics on Earth. Now, what else can you look from a spectrum? Another thing you can learn is how fast something's going. Now, we've all heard a train coming rushing toward us to then pass us, or the siren, and it comes and goes, meow. As it comes toward, the pitch shifts up. As it goes away, the pitch shifts down. With the star, as the star is coming toward us, it looks blue. as it's going away, it looks red. And with a spectrograph, we can measure very precisely exactly how much that's shifting. In fact, we can measure it to about the speed I'm walking right now, about 1 meter per second. And so it's quite amazing. We can measure how fast they're moving toward us. We can figure out what elements are on the stars. And that's why scientists like spectrographs so much. So to summarize, you can get the temperature, you can figure out what they're made of, and you can measure the motion. So spectroscopy tells us what the universe is. And I always like to think it tells us that what's way out there is the same stuff as here. It's the same physics. It's quite amazing. So now I'm going to start telling you about GHOST. Well, GHOST is a high resolution Eshel spectrograph. Now right here, you can see me quite proud that there's an Eshelgram there. What I'm going to do is demonstrate what that is by actually making the spectrograph work here. So this here, this is a grating. It's actually a transmission grating. And in there, there's hundreds and hundreds of little lines per millimeter. And what happens when the light goes through this grating is every one of those is like a different start of that. And think of them as a little water wave. So on the left, all these water waves are coming out. But if I drew exactly the right thing of those water waves coming out at a given time, I can find an angle where all those waves line up. Because light is waves, if I'm at that angle, I'm going to get some bright light, right? Now, if I put this here, and you look on the wall, you see a very bright light. And what's happening there is the light's going through here, going to the different apertures, and they're lining up. So the same wavelengths are landing on top of each other. And so the red light is all on one of those little waves. But if I change the wavelengths a little bit, it's going to change how far the waves went out. It's going to be a slightly different angle. And you're going to get that light appearing in a slightly different position. But astronomers, they need to really look at it in detail. So even though that's a big, huge spectrum there, that's not enough. Astronomers would want to take that and make that spectrum go about the whole length of the wall, so they can look in detail, find the elements that are there. So what you need is to bend the light more. And this here, on here, you see that, those staircases here? What is stairs in French? Eshel. This is an Eshel grating. There's stairs, and carved into this, there's little tiny steps in here. And when I put this, I see something that's being formed by this. But that doesn't look like a spectrum. What's happening here is because it's so steep, you have multiple instances where that same angle will form a different wavelength. So it's white because there's a red spectrum, a blue spectrum, a green spectrum, all lying on top of each other. What we have to do is spread that out. What you see right there is called an Eshelgram. And here, we go from the far blue up into the red. So the wavelength going up to here, that wavelength repeats down here. And it goes up to here, and then the wavelength repeats here. So it's kind of, I took that big spectrum and cut it up and put it all side by side. And this is very important because we have to fit all this light onto a small detector to study it. I mean, I can't buy giant long detectors like that. All my detectors are square. So we take our light from the star, we put it into this collimator, we put it through a cross disperser, we put it through this Eshel grating, And back here, we make an echelograph, a 2D spectrum. Usually when we do that, we're quite happy. And up there, you can see the echelon spectra coming out of the ghost spectrograph. And that's before we put the very expensive detector on it. So now you understand how a spectrograph works. You've seen one here, you've seen the diffraction. I'm going to start talking about building ghosts. So the ghost spectrograph itself, we designed the spectrograph in Victoria. We much of the actual mechanics of the metal was machined in Victoria up on the hill by our own machine shop, and some of it by local machine shops. And we assembled the whole thing just down the hill here in the building you drive by on the way up. And we got it all working here. We also built the enclosure for it. And of course, it takes a lot of people to do this. But now we had to ship it down to Chile. So we had to take it all apart and put it into their things. And the date was, as you can see, February 19th, 2020. And so I don't know if anyone remembers that date. We were getting quite excited, but we got everything ready to ship, and we shipped all of the metal and the big optical table down to Chile. It was about mid-March, and we said, there's something happening. There's this COVID thing. So we said, maybe we shouldn't ship the optics right away. We thought it would be a couple weeks, maybe a couple months. It was 2 years, almost to the date. And we thought we were going to be down there in April of 2020. We ended up down there in April 2022. So in April 2020, we shipped all the optics down. We got in our plane and we drove up to the observatory to start putting this together on the telescope. Now, first I have to give you a bit big of a picture here, because these next pictures I'm going to show of it going together. You kind of want to know where we are. So this is a Gemini telescope. And this here is what's underneath the telescope. And this is called the pier lab, because this big pier supports the telescope. So we want this spectrograph to be super stable, because if we're going to measure things to very small velocities, we can't have it moving around. So the best place to put this spectrograph is in the pier lab, which is way down in the bowels of the telescope. But to get the light from the top of the telescope down, we have to do that. We use fiber optics. So in the back of the telescope there, we have what we call the Cassegrain unit, and the fiber feeds all the telescope light that's fed into that blue fiber, and that goes down this big tube and into the basement. And in the basement is the spectrograph. So now here we are. We're at Gemini, and we're picking up the big optical table here. You can see the size of this. We're having to move it in, and this is the pier lab here. Now here, I'll point out this. To make this super stable, we couldn't actually have this thing sitting right on the concrete floor. Underneath there, this is this thick of styrofoam to keep the temperature. And this is called graphite JFET. It's a special type of material that can support a lot of weight, but not conduct a lot of heat. And this structure on top looks overly complicated. That's because that is in case there's an earthquake. So underneath that structure, it attaches to the table and supports it in case of an earthquake. So at that point, we get this giant table on top. And then we assembled this all up here, and we got it down there. And of course, when I pulled the plastic back, I was quite excited, because when we assembled it here, we left all of our little reference marks where the optics were up here. And I was kind of a little nervous that, you know, these might have bumped or whatever when I was shipping down or sitting in the storage container for 2 years. But luckily, they were all in the same spot, which was really nice. And then you start putting all the optics on, and you may wonder, how do you actually align them to define positions? We use these laser trackers and these special arms called a ferro arm. And using that, we can position everything on it to about 20 microns. Now remember, a human hair is about 50 to 60 microns. So we can position things really nice there. And then, of course, everyone has to have a laser and fancy telescopes and stuff. So this is what it looks like when you're aligning stuff. It starts to look kind of like a science thing. And about 3 weeks down there, we had the Spectrograph. And about 5 weeks, we had put all the other components on. And we had the big detectors on the end and all of the components on the bench. And then to keep this stable, we had to put it inside a box. This is the inner enclosure. This box keeps the air from moving around and disturbing the science. And then on top of that, we had to put it in the outer box, which is a whole box, super insulated, about that thick of insulation to keep the spectrograph stable. And soon, about 3 weeks later, those are live scientists looking at the screen. You can see all this concentration as we are all trying to decide, is it working? So what I'm going to show you next is some of the results from it. But before I have to sort of explain, because these here are the two cameras. And as you remember in that picture before, there's two big detectors. There's a one blue camera, and the blue camera makes its own blue astrogram, and the red camera makes its own red one. That's why there's two big things here. So when we actually look at a star, you can see all of these lines all the way up. And some of these lines, you can see there, that's some hydrogen. Up there is calcium, called the calcium triplet, very important to astronomers. Calcium H and K lines. But up here in this blue region, you see hundreds of little lines there. There's all these wonderful things like europium and yttrium and iron and cesium. All of those elements are showing up on this star. So it's quite amazing when you actually get to look at a star and see it in there. So now these things are not simple things to build. And you can see all the people that were involved in the project. To be very clear, in Canada, we made the bench spectrograph, which is most of the pictures I showed of the big mechanical thing. Australians, they made the unit at the top that took the light from the telescope and captured it and sent it down, right? And they also wrote software. And up there are the Chilean people at the Observatory, mostly Chileans, not all Chileans. And they were, of course, extremely instrumental in helping us to install it on the telescope and make sure that we knew to design it correctly. So there it is. Now, go ahead. Extremely good question. You see how those lines up there have different depths? Some of them are very shallow and some of them are quite deep. As the thickness or the amount of elements in the gas or the thickness of the gas becomes more, it absorbs more light and it makes a deeper line. And using that, you can actually measure how much of each of those. You can measure the abundance by measuring the depth and width of the line.
I know it's going to kind of be my question is why previously those spectrographs that show, you know, one line for G or something, why there's so many lines for one element, there's so many different lines.
Okay, so the first thing is that picture of Fraunhofer did.
Yeah.
He sketched that by hand. He painstakingly looked through there and figured out where those lines were, and those were actual ink lines that he made. So that's why there was one line there. Now, there are multiple lines for different elements because when you have a, or if you, okay, I'm not going to go all the way back, but if you remember the different orbits that the electrons can be, So if it jumps between the first and second one, it's going to make one wavelength. But if it goes between the first and the third one, it makes another wavelength, and so forth. So as you jump between the different orbits, you produce different wavelengths. And so you see this series, like the Balmer series or the Paschen series for hydrogen, and you'll see a systematic ratio between, yeah, and you see the ratio between the two lines, which is interesting because when something is expanding very fast, like very distant objects have a large redshift, so they're moving away from us. In order to figure out what element that is, we often look and see if we can find that pattern of the ratio of the wavelengths to say, ah, that is the hydrogen. Right? So they're almost like harmonics. It's not really harmonics. It's kind of like that. So those ratios always stay the same, even if it's moving away from you fast.
How much does the elemental composition vary?
Oh gosh, I might have to sit down for this. So when the universe was first created, it was mostly hydrogen, a bit of helium, and there weren't very many heavy metals, right? But as we had supernova, as we had stars burning, because what happens first, the star starts burning hydrogen, then it burns helium, then it burns lithium. And as it burns, it creates heavier and heavier elements. So we can make all these elements all the way down to almost to iron by burning in the star. But if we have a supernova or other giant events, we can make those elements heavier than iron. So because of those different processes, if I look at a star like this, it says our process benchmark. R stands for rapid. That means that this star has a lot of elements that were formed very rapidly, maybe a supernova event, that then formed the star stuff that made this star. So looking at this star, I can say, oh, this star is not a young star. It's got lots of elements, it's got lots of iron, and it's got lots of different metals. That means that this star is older, and this star probably had something like a supernova occur near what it was made of, what it was made. So yeah, you can figure out how old the star is. You can figure out the stars that were around it in the environment that formed it. And also it's kind of neat because sometimes if you look at one like cluster of stars, you'll find two different kinds of populations, which will tell you that that cluster may have merged from two different star clusters together, because you'll find some of that looks like it was made in this way and others that may be very metal poor, which is very old stars. So it's amazing detective work. And again, no touching. You got to keep your hands in the pocket. The astronomers can only look at the spectrum. Go ahead.
In what way is it important or contribute studying one particular star or different people are studying different stars? How is it enlightening how we live and what we do, what we're interested in?
Okay.
Why is it important and focus on it to understand?
That's a difficult question. Okay, so in the early days of astronomy, they would, of course, study the stars that they could study could only be the bright stars, right? And there are a lot of stars that are alike, but there are some stars that are very different, okay? And so maybe this might answer your question a bit better. Astronomers, it's difficult for them to get time on the telescope. So it's about $60,000 an hour. I think it's actually a bit more for every hour of observing time. So you have to compete to get that time. So you can't observe all the stars. So what you'll do is you'll do a lot of work at trying to understand, I want to find a star that's going to help explain something. So you might say, I think that this star cluster, you know, has had several supernovas in it. So I'm going to use another technique to find stars that might have all of these elements in it, right? And then I'll pick those stars and I'll look at them with the big telescope. So there's a lot of work that goes into deciding what star to look at. And it's not simple just to say, I want to look at that one. But if you're saying, why do you want to look at one, is because you thought about the puzzle a long time. You say, you know, maybe if we could find a star that had no iron. Right? This is a fun game with stars. They want to find the first stars, the oldest stars in the universe. So they start searching around and they look at these calcium H and K lines and they look for them to be very weak. And they do that with a simpler spectrograph and they find those to be weak. And that's an indication that that star might have very little iron. Because if it has no iron, it might be one of the first stars in the universe. And wouldn't that be fun to find? But it's, as you build up all the little things, it builds up to the greater understanding of what's going on. So I don't know if that answers your question.
So, how many stars can you image in a night? How long does it take to collect one of these spectra?
Well,
Analysis takes longer.
it depends on how dim it is, right? So stars that are in our galaxy in the local area around the sun would only take a few minutes to image. Those stars are very bright. They might be, but the stars you can see with your eyes, it only takes about 10 or 20 seconds to image that with a spectrograph. In fact, sometimes it's difficult to image them because they're too bright. Stars that are fainter, like 10th magnitude, which is, well, you say 11th magnitude, which is 100 times more faint than you can see with your eyes, right? Those stars would take about 3 to 5 minutes. But if we want to go to stars that are right in dwarf galaxies near our galaxy, so we've got our galaxy, we've got galaxies around. If we want to go to those stars, they're going to be what's about 18th and a half magnitude to 19 and a half. And those will take about an hour to 3 hours to observe. And then, of course, if you go beyond that, it could take all night. Now, what's kind of interesting is the hard part is that the fainter stars have the science we don't understand because no one's been able to look at them, right? So, but of course, it costs a lot of telescope time to observe those. So you have to sort of weigh those two things, right? It's a wide variety. And typically, astronomy is being done on about 1 to 3 hour observations for the really difficult to find signs. Yes. Oh yeah. I had an example of some stars like that. But yeah, the quasars, you see all sorts of fancy things going on in quasars. And in a supernova remnant, you'll see also the gas that's expanded out. You'll see the lines for the gas, and you'll see that they're accelerating outward and that they've been shifted. But yeah, you can look at just about anything and take its spectrum and figure out what's going on. And they even do spectroscopy of planets, comets. That's a wonderful thing to figure out what that gas is coming off the comets. Yeah, yeah, people have used that for planets. In fact, quite often they do spectroscopy on the Earth, and they do it more in the infrared, and they use that imaging on the Earth to find out, for instance, what kind of crops people are growing, and that will be in the infrared. You can figure out that, you know, whether it's a wheat crop or different types of rye, and yeah, you can look at our own planet or other planets with the spectroscopy.
Why did you choose Gemini? Why Gemini South instead of North?
Oh.
For this technology, or is there a similar one?
Well, it was going to be in Gemini North, but there was another spectrograph that was built with similar capabilities. So there was a lot of, it wasn't a simple question to put it on the north and the south. And there were many astronomers that wanted to put it on the north and many that wanted to put it on the south. But it turns out there's recently another spectrograph that was delivered with some similar capabilities. So they decided that instead of having both of the visible spectrographs in the north, they would put this one in the south. I kind of wish it was in the north, but it's also great it's in the south.
Numbers in the vertical line there, what are they? Like you've got flux. So,
Oh, that's how bright the light is. The intensity of the light. Yeah.
And then the horizontal line?
The horizontal, that's the wavelength
Wavelength.
in
In
angstroms.
what? Angstrom?
Angstroms, yes. Astronomers use angstroms and engineers use nanometers. It's kind of a competition between the two. So there's 10,000 angstroms to a millimeter. Okay, I'll take you first again.
One more question. What would you Gemini? Independently or a article that's in one and continue?
Normally they work independently because being further north, you can look to the further north in the sky, and further to the south, you can look further south. So depending on where that object is, whether it's visible in more northerly or more southerly, you pick the respective telescope you want. They are slightly different in the time. It's I think it's 5 hours difference. So in theory, you could start observing in one and then pick it up in the other, but that's rarely been done. Usually things don't have to be observed exactly at a certain time. You had a question.
You guys work like side by side or hand in hand with telescopes or something, like say if there's a star or planet or something, you know, so you guys get into that deal?
Well, very much. It's almost works in the other direction, that we observe stuff on the Gemini telescope and we find good targets on Gemini telescope and other ground-based telescopes, and then we want to follow it up with the James Webb observing, because the James Webb time is much more expensive, it's much more difficult to get, so you have to find better targets, things that are more exciting. And the second question?
So you guys check out black holes with that thing, or just because there's no light?
Oh gosh, the spectrograph and the black hole. That one, there you can see. Basically, you can see there's jets that will come out of a black hole that you can observe. But also, if you have a black hole and there's a galaxy behind it, it will form a lens, and you can observe what's behind it through the black hole. So it's like a lensing effect. And if you look at that James Webb picture, I wish I had it on the screen, not this one, but there was another one where you see a bunch of galaxies, but then you see a bunch of galaxies that are kind of distorted. And those galaxies are being actually lensed by the black hole. So then if you take the spectrum of those, you can determine that those are actually the same object, because through the lensing, it will have the same, very similar spectrum. So you can say, yes, it actually is being lensed. Okay. Well, I think we'll leave it at that. Unless there's any more questions. Thank you. Oh, thank you.
Okay. Hi, everybody, and welcome tonight. And we're very lucky to have John Pazder speaking to us tonight. Like Ben, I've known him for a very long time. And sometimes when you know people for a long time, they will do you a little bit of a favor. And I can't compete with his demonstrations tonight, but what I do have is something that that John gave me, or actually I think I bought it to him, or bought it from him rather, for a very small price. And it's actually a little meteorite, and it's from the meteorite fall that created the Barringer meteorite crater down in Arizona near the Grand Canyon. And this thing, he was talking about iron, and in the planetary bodies in our solar system, even the smaller ones such as the asteroids, the iron is often concentrated at the center of the bodies. And sometimes when those asteroids smash together, you'll get pieces flying out. And you can see that this one has a very high iron content because I have a little fridge magnet that very appropriate here. It's the solar system. I picked this up at the Kennedy Space Center about 20 years ago. And you can see that, in fact, the meteorite adheres to it because, not because the meteorite has magnetism, but because it's made of iron, and so it sticks to the magnet on the bottom end of the fridge magnet. So in any case, that's why I don't have a background right now, is I wanted to show you that cool little thing. And thanks to John for selling that to me long ago. So I'm just going to switch back and put a background up. Okay, and we'll continue with the presentation. I'm going to see if I can show you the image that he was just talking about with the lensing effect. And so this is the so-called deep field from James Webb Space Telescope, and you can see the arcs of the galaxies as they're being distorted by a large mass. They're probably black holes and dark matter and so on. And so these galaxies are not actually physically shaped like arcs, but just images that are produced that have been spread out into that shape. So I'm going to get into my presentation of something a little bit more mundane here, which is what's up in the sky. So let's see if I can switch back and stop sharing that for a second and move to something else, which is the night sky. So let's have a little look at the night sky. And we're actually going to start with the early morning. And as you can see, this is about 6:40 in the morning. I'm going to move it a little bit later, about 7:44 in the morning. And you'll notice that the moon is actually up in the morning sky. And so let's just, we'll be talking about that in just a second here. So first, the basics. The sunset was at 8:18 p.m. tonight, so 11 minutes earlier than last Saturday. And civil twilight ends at 8:51, so in just a few minutes. And you recall the definition of that was civil twilight is basically when you can move around and do most of the things that you can do in daylight. So that ends in just a few minutes. A nautical twilight, which is when you're able to see the bright stars, but not all the stars in the constellations, plus the horizon out on the ocean, that ends at 9:33 tonight. And astronomical twilight ends at 10:20. So that means that's when the sky is fully dark and you're able to see all the stars you're going to be able to see in a given location, and so on. So there's a full 5 hours and 53 minutes of full darkness, moonlight and city lights notwithstanding. And the moon phase was at last quarter on Thursday and is 33% illuminated. We're going to see if we can actually zoom in on the moon here and just have a little look at the phase and see if this actually works here. And I shouldn't experiment on these Saturday nights because I'm always getting something wrong here. But let's just try this new thing. And you can see the phase of the moon here. And so one of the things that we noted last week was that the Maria, the lunar seas, predominate this phase of the moon. So you'll notice that it just almost looks like it has a bright rim. And then there's darker areas that we can see up there, which are the big lunar seas. And so it tends to blend into the morning sky and produce this very ghostly appearance. And so also notice where how the moon is oriented here. You can see that you would think the sunlight's coming from this direction. And in fact, if we zoom out here, you can in fact see that the right angle to that is pretty much down to the sun over there. So as you'd expect, that's why it has that phase. So we're just going to switch to the evening sky now. So we're going to actually just jump, I think, to, if I can do this right, we're going to, no, let's just stop here. We're going to actually try to jump to present time here, up in the nighttime sky. And I'm going to zoom out just a little bit more. And so you can see down on the southeast horizon that Saturn is coming up. It's still twilight right now, as I was just saying, but Saturn is coming up, and it rose at 8:02 and Jupiter is rising at 9:35. So we'll just skip ahead to that time and just see if we can do that here. Having a little bit of a few technical difficulties here. So we're going to skip ahead, and we should see Jupiter rising up right around then. And then Mars comes up at 11:35, so we're just going to advance up to about that time, and that's closer to the east, so we're just going to see if we can scoot it up a little bit, and we should see Mars coming up. It's a little bit further to the north rather than the east cardinal point, so you have to look quite far to the north rather than looking down in the southeast like you do for the other planets. So in the morning sky, Venus rises at 4:43 a.m. after twilight has started. And as far as other things up in the sky this week, this has been a busy week for seeing the aurora. The Earth was hit by several geomagnetic storms, and aurora were visible from Vancouver Island. And as we continue to move towards solar maximum in a couple of years, keep your eyes peeled for announcements about possible aurora on sites like spaceweather.com, which is my personal favorite. And in fact, there should be, I think there was a geomagnetic storm that started earlier today, and we're expecting another one. So tonight might be a good time to actually see the northern lights. And so let's just have a little look here at the Milky Way, and I'm just going to try to zoom out and then try to look at the whole sky here. And I'm just going to get the time out of the way here. And also going to see if we can get rid of some of the light pollution effects, and I'm just going to, and some of the sky glow by getting rid of that. And so you can see in the evening sky at this time of the year that the Milky Way, which is actually quite bright down towards the south, extends right overhead in the late evening. And so one of the things that I love to do at this time of the year in August, because it's warm out and you can spend a lot of time outside, is just to lie on my back with a pair of binoculars and scan right overhead at these star clouds up here in the constellation Cygnus, and then further down towards the constellation Perseus. And you can see there's still a few Perseid meteors dribbling in. There was some reference to the center of the Milky Way, I believe, the black hole at the center of the galaxy. And I can show you where that spot is, if I can do this properly. And so you can see that there's sort of a triangle of three fairly bright stars down here. And I'm just going to get some of these star names out of the way if I can. Okay. Let's see if we can do that. Okay, I don't think I'm able to there, but the center of the Milky Way is actually over in this nondescript area, which is quite dark. And so you won't actually see a lot of star clouds in that direction or any bright stars, but it is in there, and it's simply hidden by the vast amount of dust that's blocking our view. And so, of course, to get a picture of the black hole, what they had to do is they had to go to other wavelengths that could effectively see through all of that dust in order to make the images. And so they were made at the sub-millimeter waves, and at that wavelength, the dust is essentially transparent. One other thing, I was asked this earlier this week online about what a very mysterious train of objects that was moving through the sky, and asked if it was a UFO or something. And it certainly did look very unusual, but in fact, it was just the Starlink satellites being launched. And so they sort of play follow the leader and go one after the other across the sky just after launch. And if you're ever wondering about that, there's a great website called Heavens Above. It's just www.heavens-above.com. And on that site, you can, if you've seen say a satellite the night before, you can set it back in time and look at the satellites visible for your location. So remember to set your location when you do that. That's all important for being able to see the satellite, identify the satellites that you saw, because they're not very far away, they're only a few hundred kilometers up above us. So it's super location specific. So I think that's about it. That's about all I have to share with you tonight. And I just wish everybody happy observing, and just remind you that we're a volunteer organization, a nonprofit that really appreciates donations and memberships, and also visit our our gift store, and I told a colleague this week about our organization, and he said, "Well, he said I got one question." He says, "I like to buy stuff. Do you sell anything?" And I said, "Oh, our treasurer would love you."
That's perfect.
So of course, Amy, I gave, it was during work time, but I gave him the link. So hopefully he bought a
Awesome.
bunch of stuff.
Awesome.
So yeah, if people watching on YouTube, if you're not members yet, please go to centeroftheuniverse.org and join up. We really appreciate your support. And so Amy, do you have any questions or anything you want to talk about?
No, just a reminder, if people are in Victoria, of course, that or even if they're visiting Victoria, that until the 29th of September, we are open Tuesday to Friday from 10 to 2. And there's just a very nominal fee to come in, but but come on up, and there's tours of the dome, and it's a little bit of a different layout than on Saturday night. So we'd love to have everyone.
For sure. And it's a time maybe to ask more questions and just explore at your leisure and so on. Now, I have to ask, do you have any cool fridge magnets in stock like this? Or I don't know if you probably don't have this one because this is a NASA one, but.
We don't have that one. No, we have some moons. We have some moons, and we have some pictures from CFHT.
Oh, okay.
But not as cool as that one.
Yeah, this is actually one of these kind of 3D
I
kind
love
of things.
that.
Almost looks handmade or something like that.
Yeah.
So yeah, you'll have to get on that, Amy. So
yes, but right now I can say that we have more and more of the celestial buddies. If anybody needs a planet to cuddle up with at night, and we even have a Polaris that lights up. Just pretty cool.
That's pretty cool. Everybody's favorite Cepheid variable, right? Polaris. Yes. Does it vary in brightness like the real one does?
Does not, and we don't have the AB. There's another one that I think I'm going to be getting that has two, like the AB, Polaris A and AB, but not yet.
Well, we'll have to come up with a deluxe version of that.
Exactly.
Vary a little bit in brightness. So yeah. Okay. So I think that's about it. So yeah, just keep looking up, everybody. Come on up. It's a really positive organization to be part of and visit. So love to see you.
Yes. Thank you.
Okay. Good night.
Good night.